Namaskara. We have been looking at the properties of the minimum weights of the shortest paths. We are looking at the single source shortest path problem from the source to other vertices. We are interested in finding the shortest path. Towards that, we are looking into the mathematical properties of the minimum weights or the weights of the shortest paths. If G is an instance of the single source shortest path problem, and if delta V is the weight of shortest path from S to V, then we have derived the following equations when G has no negative cycles. When G has no negative cycles, we have proved that delta S equal to 0 and delta V equal to minimum over the edges, all the incoming edges UV, minimum over UV of delta U plus weight of UV. We can extend it and make it simpler looking by adding other conventions, but in a sense this is the equation called Belman equation, and we have seen an example where if G has 0 cycle, this equation allows us to have infinitely many solutions, and if G has a negative cycle, of course these equations do not make any sense, and as expected it does not have any solution. We have also shown the non-existence. Okay. To summarize, here is the theorem: let G equal to V E W S be an instance of single source shortest path problem if G has no negative cycle or 0 cycles, then the equations x s equal to 0, x v equal to minimum over all the incoming edges u v over x u plus weight of u v, this is small v, has a unique solution and the unique solution is x v equal to delta v for all v belonging to v. This is that unique solution. Okay. And this gives us, I mean, assuming that we are able to solve, we are getting the weights of the shortest paths. But what we want is not only the weights of the shortest path, we want those paths themselves. How do we explicitly obtain the paths with this length? We have to look into that, and fortunately the solution contains enough information about the shortest path itself. Okay. So, in the unique solution for a vertex v, we will have xv equal to xu plus weight of uv for some edge uv. This is an edge incoming to v, or it is an edge ending at v. Okay, it is like this. This is u and this is, it's an edge ending at v. So, this is how the solution is. If you look into the final solution, it will have this form, and we call this edge uv, which is ending at v, as the Belman edge corresponding to the vertex v. This uv is called Belman edge corresponding to v. Okay. In the solution, there is an edge that is ending at v, and that edge is called Belman edge. So, for each vertex there is only one edge, because in that solution we have an edge ending at that vertex. So, one Belman edge for each vertex, but if you look at S, there is no edge ending at S. In fact, delta S is straightaway set as 0, there is no Belman edge associated with it. So, for all vertices other than S, we have a Belman edge associated with this. Therefore, if cardinality of v equal to n, other than S there are n minus 1 vertices, for each vertex v not equal to S, we have an associated Belman edge uv. Therefore, there are n minus 1 Belman edges. These edges are edges of the graph, okay, and there are n minus 1 Belman edges. We construct a graph, it is called the Belman graph associated with G, because from G you form the Belman equation, and then when you solve you get these edges identified as a part of the solution. So, what is a Belman graph? Belman graph B associated with G, you can say the same vertex set, BG is same vertex set, and the edge set is the set of all Belman edges. Okay. The edge set E dash is set of all Belman edges. So, this is a graph with same vertex set, but only n minus 1 edges. Okay. We are going to show that this graph is in fact a tree. Okay. There are no cycles. First we will show that there are no cycles. In fact, it is a directed graph, therefore, it is a tree like structure, and this is called out tree. Out tree means from the root all edges will be directed towards the leaf. This is the root, all edges will be like this. This is the root, S is going to act as a root, and to all other vertices we are going to have paths. Okay. We will show all of them. So, this Belman graph is going to be this BG, we will show as in fact an out tree. Out tree means from the root all edges are directed towards the leaf. In tree means all the edges are directed towards the root, they will all go towards the root. Here all of them are going away from the root, okay. This is called out tree. We will show that this is basically an out tree. First we will show that there are no cycles, okay. BG has no cycles. Suppose it has a cycle, right. Assume that BG has a cycle. Let C equal to V0, V1, V2, Vk, where Vk equal to V0 be a cycle in BG. Assume that there is a cycle. We are going to arrive at a contradiction, okay. We are going to arrive at a contradiction. So, the C is like this, starting from V0 to V1, V1 to V2, V2 to V3 and so on, Vk minus 1 to Vk, and Vk is nothing but V0, Vk is V0. It comes back. These are all the edges in the Belman graph. Therefore, you have V1 delta V1 equal to delta V0 plus weight of V0 V1. This is equal because it is a Belman edge, right. This is a solution, therefore, we have this equality, and delta V2 is delta V1 plus weight of V1 V2. So, in this way we are going to have for each edge an equation, right, and finally delta Vk equal to delta Vk minus 1 plus weight of Vk minus 1 Vk, right. For each edge we have an equality. You add all of them, all right. Here you are going to get weight of V0 V1, weight of V1 V2, weight of Vk minus 1 Vk. So, you are going to get the weight of the cycle, right. You are going to get the weight of the cycle when you add all of them. So, here adding you get sigma I equal to 1 to k of delta Vi is equal to sigma I equal to 0 to k minus 1. Here V0 to Vk of delta Vi plus weight of the cycle C. All these things they add up to weight of the cycle C. All the edges of the cycle are listed here, their weights are added. So, you get the weight of the cycle there. But these two terms are equal, therefore, you can cancel them. Why they are equal? If you look at V1 to Vk, right, delta V1 plus delta V2 up to delta Vk is same as delta V1 plus delta V2 plus delta Vk minus 1 plus Vk is V0, delta V0. Bring this V0 here, you see that this is delta V0 plus delta V1 up to delta Vk minus 1. So, that is what is there on the right hand side. So, this implies sigma I equal to 1 to k, this is I equal to 1 to k of delta Vi is same as sigma I equal to 0 to k minus 1 of delta Vi. Both terms, they are same values. So, you can cancel them out. Okay. So, when you cancel them out, you get 0 equal to Wc, implying that C is a 0 cycle. But we have assumed that we do not have a 0 cycle or a negative cycle in the graph. Okay. Our graph has no negative cycle, no 0 cycle. Only on such graph we can formulate this equation and then attempt to solve. So, we are assuming that G has that property. C has a 0 cycle, contradicting the assumption that G has no 0 cycle. We have assumed that G has a no 0 cycle, but here we are showing a 0 cycle if we assume that Belman graph has a cycle. Therefore, Belman graph has no cycles. Okay. Since Belman graph has no cycle, we get the following consequence, right. Let us take any vertex V, take any vertex V other than S, okay. S has no Belman edge. So, there is a Belman edge ending at V. Let us say U V is the Belman edge ending at. For U, there is a Belman edge ending at U, let that be W. So, in this way this chain keeps going backwards, okay. This chain keeps going backwards. Every time you are going to see a new vertex that is not considered already. When you go back, you will keep finding newer and newer vertex. Why? You will never encounter a vertex that you have already visited. If it so, it forms a cycle. Let us see, from V you have come to from U you have gone to V, from W you have come, from say from T you have, but to T, suppose you have come from one of the already visited vertex, then it will be like this, right, and this is going to form a cycle. Such an edge will not be there, therefore such an edge will not be there. To T probably you will come from some other vertex, okay, some L. It will all be newer vertices. Every time you are going to come from a distinct vertex that is not encountered in our backward journey. Therefore, when you keep on getting your, at some point you will get S. There is no cycle, and then every time newer means some, so it is going to be like that. From S you can't go any further backwards because S has no Belman edge ending at S. Therefore, the process would stop at S and things will look like this. When this backward extension stops at S, we see that there is a path from S to V in the graph. So, for every vertex there is a path from S to that vertex. Therefore, it is going to be a out tree, no cycles. This path is called PV. In fact, this path is a shortest path from S to V. Therefore, these Belman edges sequenced like this, they lead to a path. That path is in fact a shortest path. Okay? Why this path is a shortest path? You have a selection of edges and they go to S, but how come they constitute a shortest path? The proof is simple, very similar to the argument that we have given for cycle. We will let us say our we have a path from S to some vertex and from there to some vertex and so on, and finally somewhere to V. We have seen that such a, just for the sake of ease of reference, we call this S as V0, the next one as V1 and the next one as V2, and V itself will be Vk for some k, okay. Because it is a path, we name it like this so that we refer the edges as V0, V1, V1, V2 and so on, so that it becomes easy to do index based computation, okay. Now in this Vi minus 1 Vi minus 1 Vi is a Belman edge. Okay. Therefore, we have delta Vi is equal to delta Vi minus 1 plus weight of Vi minus 1 Vi. Weight of Vi minus 1 Vi. This implies weight of Vi minus 1 Vi is equal to, move the delta V, so delta Vi minus delta Vi minus 1. Okay, I have moved delta Vi minus 1 to the other side. So for each I have this equality. What is the weight of the path? Weight of the path is, let us say this is path PV. Weight of PV is weight of V0 V1 plus V1 V2 plus V1 is equal to sigma I equal to 1 to k of W Vi minus 1 Vi. That is equal to sigma I equal to 1 to k of dVi minus dVi minus 1, because Wvi minus 1 Vi is dVi delta Vi minus delta Vi minus 1, not d, it is delta, I am sorry, it is delta. The sum on the right hand side is called the telescopic sum, okay. Sigma I equal to 1 to k of delta Vi minus delta Vi minus 1. How does this look? For I equal to 1, it is delta V1 minus delta V0 plus, for I equal to 2, delta V2 minus delta V1 plus delta V3 minus delta V2 and so on. Finally, for k it is a delta Vk minus delta Vk minus 1. Here delta V1 and delta V1 cancels, delta V2 and delta V2 cancels, and in this way all of them will cancel except Vk and V0. Therefore, this sum is actually delta Vk minus delta V0. Vk is V, right. Therefore, this is equal to delta V. V0 is S minus delta S, but delta S is 0, therefore, this is equal to delta V. In other words, weight of PV is delta V. That shows PV is a shortest path from S to V. So, all you have to do is that while solving the equation, you not only obtain the delta V values, there are edges whose weights define those equations, just save those edges, and those edges are useful in constructing the shortest paths. Okay? Just those n minus 1 edges you hold, that is enough. They are all useful in constructing the shortest path. But if you hold them in a messy way, constructing the shortest path would become hard. So, we are going to maintain it in a very simple and an elegant way. Okay. It is based on the following observation. If you look at the way in which we have derived the equation for delta V equal to delta U plus weight of UV. This is the shortest path, this is the shortest path, and this is the last edge in the shortest path. So, from S UV, this is the last edge. Okay. Therefore, U is a vertex previous to the vertex V in that path. All we are going to do is that we save the edge in the following way. For each V, we maintain the previous vertex. So, U equal to PV. So, for each vertex there is only one previous vertex. Therefore, I can use an array indexed by vertices. P of S is undefined. There is no Belman edge. There is only one Belman edge for each vertex. That edge is ending at V. So, if UV is a Belman edge, then previous of V is defined as U. Now, for U there is a previous of U. That is how that chain was constructed. There is a Belman edge ending at U, that we have considered, that will be previous of U, and for the other one there will be. So, for V this is U, this is previous of U. For U there is a W, that will be previous of U. This is previous of V. For V this is previous, for W is previous of U, for W there might be some T which is previous of W. In this way it goes all the way up to S. S has nothing previous to it. This is the path PV. So, this P of U now can be written as P of V. This P of W can be written as P of V, because this is one vertex, its previous is this, and so on. So, if you have a previous array, you keep looking into the previous array and keep obtaining the sequence of vertices. First start from V, go to P of V, from there go to its P, which is denoted as previous of V, P of V. From there again go to P of V. Keep going until you get S, right? Then you are going to get the vertices of the path. What is the actual vertex sequence of the path? it is V, P of V, P of V and so on up to S. Okay. So, this is how you would get starting from V, keep applying the P function or P array entry consultation until you hit S. S has nothing previous to it, so you are going to stop there. But this is outputting the vertices of the path in the reverse order. What you want actually is the path from S to V, the shortest path from S to V. But those vertices which are in the shortest path are obtained in the reverse order. So, in order to output properly P of V, what is that you should do? Print this in the reverse order, generate it, but print it in the reverse order. For example, if you want to have a linked list of vertices of P of V, how can you create that linked list? It is very simple. First L, this is a linked list for P of V. First it will point to V. Insert in the beginning of the list, then L, this P of V will become P of V and that will point to V. Insert, find P of V, but insert at the beginning of the list, always insert at the beginning of the list. Then P of V will be a list pointing to P of V, this you have found out. This is inserted in the beginning and so on. So, finally P of V will be a list pointing to S. When you find S, you insert it. Finally, it will have V. You can see that this linked list is in fact containing the vertices of the path PV in that order. That is because I have inserted in the beginning, it is a kind of reverse growth. Therefore, as you see the linked list, the vertices are appearing in the natural order from S to V. Therefore, we are going to only construct P of V. P of V is used as and when required, as and when you require a shortest path, that P array will be used to actually build the path. I am not going to output the paths, I am going to output only P of V. If you require physically the path, you generate it starting from the vertex, apply P of V, P of V and so on, go to S and output those sequence of vertices, you have the physical path. Therefore, paths are not explicitly output, paths are implicitly output through P array. Okay? The P array is called parent array or previous array, parent array or previous array, this is the name or interpretation of this P array. P array is called implicit representation of shortest path. Okay. Why it is called parent? If you look at the Belman tree, okay. So, this is how the path V, parent of V, this is U, UV is an edge, and for U, let us say WU is the Belman edge. This Belman edge tracked backwards go up to S. Therefore, it is an out tree. In that out tree, U is a parent of V. For V, I maintain only one piece of information, namely its parent, that is all. So, every vertex has got only the pre or parent information. With this information, you can explicitly construct the path by chasing the parent array pointers or parent links up to S, up to the root. Okay? That is the reason why this is called implicit, means hidden. You are not giving for every vertex the long list of vertices of shortest path. For every vertex you give only P of V, that is all you are giving. Okay? Therefore, our goal is, given G equal to V E W S, G has no negative or 0 cycles. This is given that G has no negative cycles, output delta V P of V for all V belonging to V. We know that delta S equal to 0, P of S is undefined. There is no previous to S, this we know. All others we compute and solve, right. We solve Belman equation and then we can compute it, and in this way we would proceed. Okay. So, this completes our discussions on Belman tree. In fact, Belman tree is also known as shortest path tree. Belman tree is also known as shortest path tree. Because the path in the tree from S to a vertex is indeed a shortest path, but I am not explicitly representing the tree, I am representing the tree using a single array. For each vertex I maintain only the previous vertex in the path. Okay. This compact representation allows us to build efficient algorithms, and as and when you need the path explicitly, use the P array and construct the path as outlined earlier. Okay. So, this completes our discussions on Belman equations, Belman edges, Belman trees and shortest path trees, and this allows us to represent our goal in a more concise manner. Here is the clean statement of the single source shortest path problem. Thank you.